Wildcats.
Oh. Hi, Wildcats. Mr. Weber here with my niece and nephew. Say hi to everyone.
Hello.
Your name is?
Hannah.
And your name is? Say hi to everyone.
Hayden.
What? Say hey, hi there.
Hi.
What's your name?
Hannah.
Your name's Hannah?
Yeah.
I thought that was her name.
That's my name too.
Oh, well, this is Hannah and Hannah, also known as Crazy Hayden. And we're going to show you an example of how you can make forces video. We are there's on a sled. I am going to pull on this sled, and they both are a mass, so they'll accelerate when I apply a force. So we need to know what their masses are. Hannah, what's your mass? What's your weight? 63. Do you know what that is in kilograms?
No.
Okay.
What's
yours again?
Kilograms?
What is kilograms? It's a better system of measurement. Don't worry about it. Hayden, what do you weigh? 46. Okay, 46. And then, so 46 pounds or kilograms? It's 6. Okay, that's pounds. And then I measured the sled before, and it weighs about a kilogram, 1.5 kilograms. There's some things that we're going to have to make some assumptions about here. One, that we're going to assume that the ground is perfectly flat, which it probably isn't. We'll also assume that the kids are one mass. And even though when I pull on this, it'll probably be at some angle, I'm going to do my best to keep it perfectly horizontal so we don't have any angles to worry about.
What is horizontal?
What is horizontal? It means flat.
Why do you keep saying words that I don't even know what they mean?
Well, why don't you know the words, the meaning of the words that I
Because
say?
you teach high school.
Well, what grade are
I'm
you?
only 7 in first grade.
Only in first grade. Well, it's not my fault that Grove Elementary, which feeds into normal community, isn't as good as the West Side elementary schools. Be nice. Don't hit me. Okay, calm down. The one other thing we need to know is the coefficient of friction between the grass and the board. I looked that up online. It is about 0.64. What's friction? Why do you have so many questions?
Because I like asking.
Yeah. So I have Google Science Journal on my phone, and I have it set to the X accelerometer, the horizontal accelerometer. And Hannah's going to hold it while I pull them, and that'll allow me to know the acceleration of this.
I'm also going to say potato.
You're going to say potato? What do you think about the Wildcats?
Taco, and I'm also going to say taco. They're 3,500
Something. You're saying taco and you're saying potato. This is a great experiment. Okay, are you ready, taco and potato?
Yes.
Are you sure?
Yes.
Okay, you got that? Hayden, are you ready? Hannah, are you ready? Hannah, 2, are you ready?
Yes.
Okay, 1, 2, 3. That's as fast as I can go. All right, can I see that? All right, stop. So I have my acceleration data. My participants are running away to dance in the yard and do other things. So I hope everyone is well, and we'll talk about the math in the other part of this video. Thank you. Hi Wildcats. So I just got in from the wind, and here is, I've given 2 screenshots of the data I collected. The one on the left is just the raw data, so that whole experiment from the time I pressed play and handed it to Hannah until I picked it up from her and pressed stopped took about 18 seconds. So you can see here's the data. This first section from here to here looks like when I was handing it to her, and then the time when she was holding it still. So we don't care about that. And this section at the end is where I picked it up and turned it off, so we don't care about that. So really, from kind of timing it out in the video, it looks like I started pulling around here and ended around here, so about 8 seconds worth of data. So that's really what I want the average acceleration of. If you are using Google Science Journal, at least on Android, you'll be able to crop the data down. So that's what I did. I cropped it to here. This is just the 8 seconds where I was pulling them across, and it tells me the average x acceleration is -1.1. The negative is just direction, so we don't necessarily care about that. So really, from this analysis of this data, it looks like they were accelerating at a rate of 1.1 meters per second squared. So now that I have that, I can go in and start calculating my forces. Alright, so now that we have our acceleration data from Google Science Journal, we can start working out the specific magnitude and directions of the forces. So net force is going to be the first one that we solve for. We know Newton's second law is acceleration is equal to net force divided by mass. So then I can just rearrange that. Force net equals mass times acceleration. So I have both of those numbers. So F net will just be equal to the total mass. I went and did the math ahead of time. Hannah had a mass of 63 pounds, she said, or 28.6 kilograms. Hanna 2, also known as Hayden, was 46 pounds, so 20.9 kilograms. And the sled had a mass of 1.5 kilograms, so total mass of all of them combined was 51 kilograms. So we would just do 51 kilograms times the acceleration that they experienced due to the force that I applied, which was 1.1 meters per second squared. So F net is equal to 56.1 newtons. So the total force on them was 56.1 newtons. So now we can start looking at the individual components, forces that make that up. So easiest one is going to be force of gravity. It's just the total mass times the acceleration due to gravity. So 51 kilograms times negative 9.81 meters per second squared. Force of gravity for them is equal to about 500 newtons. And that's down. So we've got the force of gravity is minus 500 newtons. We know that normal force is equal to the opposite of the force of gravity. So then normal force would just be plus 500 newtons. We can figure out the force of friction. We know that it is equal to the coefficient of kinetic friction times normal force. So I said from my research the coefficient of kinetic friction was 0.64 for plastic on grass, and we know that the normal force is about 500 newtons. So the force of kinetic friction in this case is minus 320 newtons. I get 320, but when I look at my free body diagram, I see that it's to the left, so therefore it's going to be negative 320 newtons. And force applied is, it's got to be greater, right? Net force is to the right because they accelerated to the right in that video. So I can think about this as the net force is equal to all the horizontal forces. So in this case, it's force applied and the force of friction. So to find force applied, I just subtract the force of friction from both sides. So force applied would be equal to F net minus the force of friction. And in this case, F net we figured out was 56.1 newtons minus the force of kinetic friction, which is minus 320 newtons. So 56.1 minus negative 320, I ended up with 376 newtons. So it looks like I pulled on the sled with 376 newtons of force. Friction was in the opposite direction, 320 newtons, which gives me a total net force of around 56 newtons. Okay, so hopefully that helps kind of give you an example of how you could work through and think through a video that you create. Some tips for you to consider as you're planning out what you want to do. 1, don't use angles. So I made a point of pulling horizontally. If I did this at an angle, I would need to resolve for the components, which we don't like, but on top of it, I wouldn't be able to determine the applied force without a force meter, which I'm assuming none of you have at home. So if you're going to be applying a force, I would make sure you do it either straight horizontally or straight vertically, because then you avoid having to know what the applied force actually is. You can just figure it out like we did here. I would also avoid things with wheels. Rolling things include rotational motion and a bunch of other calculations that we haven't done. So it'll probably make your life easier if you don't use something with wheels. And I want to stress again, I put it in the instructions. This approximations are okay. I'm not interested in you learning a bunch of technology for this other than being able to maybe use an app. I'm not interested in you taking the world's most precise measurements. I just want to see that you can approximately determine the forces acting on an object when it accelerates in real life. So please don't stress over the minor details or getting absolutely everything perfect. We just want to make sure that that's about correct. So for example, I just did a quick look. The average human can pull with between 400 and 600 newtons of force. So the fact that I did 376 seems about right. If I had gotten 3,000 newtons, I would probably question something or some calculation that I did. So you just want to come approximately close, and that'll be just fine. So as always, do your best. Everything will be fine. I'll have a help session this week. So if you're confused, you're having difficulty, you're stuck on something, please join that or shoot me an email, and I will be happy to help. So good luck, and remember, have fun.